My dear students, now we are going to look at 3-bit up counter. We try to see how to design the up counter. So in the problem given itself, it says that it is a 3-bit up counter, right? So 3-bit up counter will have 3 bits in its output. So generally, any counter design, or to be specific, synchronous counter design, we have specific process. So whenever there is specific process, it is better to represent in steps so that we will not miss any of these steps so that we can complete the design properly. So first what we try to do is we try to find for the given counter, we need to find how many number of flip-flops required. Number of flip-flops required we try to look at. Once the number of flip-flops are clear, how many flip-flops that we require, then we can proceed with those many number of flip-flops. Generally, for a 3-bit up counter, the problem itself is saying that it's a 3-bit up counter. 3-bit up counter, right? So in a 3-bit up counter, we have 3 bits of data. For each bit, I need a flip-flop. For 1 bit, 1 flip-flop required. For 1 bit, 1 flip-flop required. For 1 bit storage, if I want to store 1 bit, to store 1 bit of data, I need 1 flip-flop. Because I have 3 bits, I need 3 flip-flops. It is very straightforward. But in certain problems, it is given as mod number. Say mod 5 counter, mod 10 counter, or in general mod n counter. Okay. So in such case, also we need to determine number of flip-flops required. How to do that? I will give you the formula. Okay. So what is this mod number? Mod 5, if I say, it is going from 0, 1, 2, 3, 4, then 0, 0 to 4, totally 5 different states, which counts from 0 to 4. Actually, mod is modulo operation. So what is that modulo operation? Is repetitive in nature. So 0 to 4, mod 5 is 0 to 4, 5 different states. Then once again 0 to 4, 0 to 0 to 4. That is called modulo counter. In short, it is called mod. That's fine. So if it is a 3-bit counter, it will go from 3 zeros to 3 ones. How many different states we are going to get? Here we are going to get the different states as 8, starting from 0 to 7. So it is called modulo 8 counter, in short mod 8. So 3-bit counter is nothing but mod 8 counter. Okay. So whether it is okay 2-bit counter, 3-bit counter, 4-bit counter, or 5-bit counter, or mod n counter, first thing that we need to do is in a synchronous counter design, we need to find the number of flip-flops. What is synchronous counter design? Synchronous counter means it has a common clock. Clock is same. Common clock signal. If clock is same, then it is called synchronous. Okay. Then in a problem, they may give the flip-flop. Which flip-flop to use? Whether to use JK, whether to use D, whether to use T, or whether to use SR flip-flop. Okay. So whatever the flip-flop they are asked, like in the problem, if they ask particular flip-flop, you can use any one of the flip-flop. You can use any one of them. But generally, prefer to use T flip-flop. T flip-flop is toggle flip-flop. This toggle flip-flop is developed for design of counters. So your problem will be simple, easy. Even if you are using the other counters, maybe if you are using JK, T, or D, or SR other than T. For counters, by default we use T flip-flop. Even if you are using other flip-flops, we do convert this into T and in the process of design. Okay. So if any counter, if at all you are using JK in a counter, we will be using JK as T. Okay. If you are using D, we are using D as T. If you are using SR, we are using SRT. Okay. In the design, we get those expressions. Okay. We don't convert it, but In the process, it will get into converted into T, then it will get used. Okay, so that is what exactly the thing. So in general, for counter, okay, if nothing is mentioned, you can use T flip flop, which will make your design simple and easy. Okay, there is no any restriction to use any other flip flop, you can use it. Once that is clear, so second is step 2 is you take a T flip flop, or you take as per the problem statement or for the problem description. Then based on the requirement, based on the requirement of the problem, what we try to do is we draw the state diagram. What is state diagram is, let's suppose a 3-bit counter. So now I draw the state diagram. So it will be going from 8 different states. Okay. Zero 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 one 010 011 100 101 110 111. So in the present state of this, it will go to the next state. This from this state it will go to the next state. From this state is going to next state. From this state is going to next state. If from this state is going to next state. From this state is going to next state. From here to here, then here to here. After all once it will go to. This is called state diagram. What is this? This is a state diagram. So from the state diagram, what I try to do is I try to draw. What I next that I do is what I do is here I call it as state diagram. Next what we try to do is, what is this step? This is step number 3. Once step number 3 is done, next we will go to step 4. What is step 4? Step 4 is, okay, step 4. What we will do in this is, we will develop excitation table for the counter. Okay. So what is our counter? Our counter is very simple. Present state, next state, and flip-flop inputs. What exactly the flip-flop inputs, such that it will go from one state to other state. If it is at 000, it has to move to 001. If it is at 001, it has to move to 010. Okay. So you have a flip-flops, 4 flip-flops. How this flip-flop, 4 flip-flops has to behave? For which we will give a common clock. Clock is common. This is clock. How the clock look like? It is going like this. Okay. If I give the clock, what exactly is happening is, here we are having only 3 flip-flops because it's a 3-bit up counter. So we don't require, okay, 4. We do require only 3. So initially what is the content of this is 000. Next it has to become 001. Next it has to become 010. Likewise, it has to change the content of this flip-flops. For that, what we are trying to do is, with respect to the inputs and outputs, here we are getting output, output, output. So what we try to do is, we have to give the appropriate input to the flip-flop such that currently if it is in at 000, it has to move to 001. So I need to give the input such that it will move to 001. So what we try to do is, we look for what flip-flop inputs we are supposed to give such that it will have a specific transition. What is the specific transition is? Flip-flop A, flip-flop B, flip-flop C. It has 000. Now this is the next, it will go to the next state. The next state that looks like 001. Then I can say that the present state 02 it is going to next state 1. That means 00 to 1. Then if the present state is 001, it will go to 2, so 010. If the present state is 010, it should go to 011. If the present state is 011, it should go to 100. If it is at 1 0 0, it should go to 1 0 1. That is what exact state diagram I have shown. If it is at 1 1, say if it is 1 0 1, it should go to 1 1 0. If it is at 1 1 0, it should go to 1 1 1. Okay. So next, if it is at 1 1 1, it should go to 0 0 0. So cycle repeats. This is called up counter. What is Y up counter? I up counter is for 0 it is going to 1, for 1 it is going to 2, for 2 it is going to 3. So 2 to 3, 3 to 4, 4 to 5. So it is going up to 7. Okay, 0 to 7 totally 8. It is called mod 8 counter or 3-bit up counter. Okay, now let us suppose I am using 3 flip flops TA, TB, TC. Now if you want this transition in the flip flop state, flip-flop state. So what is state? State stands for memory. The word state is used wherever you refer to memory. Wherever there is a memory, we use the word state. So present state means present memory. Then next state is next content of the memory. How exactly the memory will be get updated through flip-flop inputs. So we have to give some excitation to the flip-flop input such that, okay, it will move to, if it is at right now it is 0 0 0, it should become 0 0 0 1 after application of the clock. So then what exactly required is we do compare what exactly I need to give a TA such that it will move from, for QA plus 1 next state. It is 0 1. If TA is 1, it is possible. If earlier if it is at 0, it can move to 1. How can I say that? It's very simple. For the T flip flop, what is excitation table? Qn plus 1 and TA. As long as these are same, TA is 0. That means for 1 1 0 0, TA is 0. For 0 1 or 1 0, then input should be 1. Now what is the meaning of this is, if present state and next state are same, then T input is, present state and next state are same, T input is 0. If present state is different from next state, Qn is present state, Qn plus 1 is next state. If present state is different from next state, TA should be 1, input should be 1. So here it is changing, means TA should be 1. If TA is 1, this transition is possible. That means it will move from 0 to 1. Okay, for QA. Similarly, if I look at 1 0, 1 0 means changing, 1 0 1 1 0 0 1 1 0 0 1. Okay, then 1 0, always opposite. So that means TA is always 1, TA is always 1 1 and also 1. Once this TA is 1, what about TB? Compare this QB with QB plus 1. What we did earlier? We have compared QA with QA plus 1. Now if you compare these two, upon comparison of these two, I will come to know what input I should give it to TB. So when this is 0, this is also 0. So no change, 0 from this table. For 0 0, it should be 0. So for 0 and 1, for 0 1, here for 0 1, input should be 1. Whenever there is a change, it should be 1. If they are same, 0. So here it is same. So third one is 0. Fourth one, it is 1 0. So it is 1. Fifth one, 0 0, no change. 0 1, 0 1 means it is 1. Next 1 1, no change. 1 0, change 1. From this table. From which table? Excitation table of the flip flop. Right? So next what I need to do? What I need to do is, I need to compare QC has to be compared with QC plus 1. Compare this two. 0 0, 0 0, 0 0. So it is 0 0 0, 0 1. So input should be 1 from this table. Okay. So from here, from T flip-flop excitation table, we are getting excitation table for counter. So what is this is excitation table for what exactly? T flip-flop. What is this that I am doing? Excitation table for counter design. Okay, synchronous counter design to be specific. So counter design. So now this is one, 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 this is one. That means three consecutive zeros. For 1 1 or 0 0, for 1 1, the TA should be 0 from excitation table of T flip flop. So next for 1 0, it is. Now we got the points. Now we can write the expression for TA. TA is nothing but sigma m 0 1 2 3 4 5 6 7 and 6 7, totally 8. What is TB? TB is 1. Okay, if you want that serial numbers, you can write here 0 1 2 3 4 5 6 7. It is 1 for 1, it is 1 for 3, it is 1 for what exactly? Alternatively. Alternatively is 1, it is 1, sigma m is 1. For 2 it is 0, but it is 3. Next for 4 it is 0, for 5. So for 5 it is 1. Okay. And for 7 it is 1. Right. Similarly, you can look at TC. TC is sigma m. For which values it is 1? It is 1 for 3. It is 1 for 7. So sigma m 3 comma 7. From these values, what I can do is I can get expression for what are the inputs? From QA, QB, QC, I need to get TA, TB, TC. Though it is flip-flop inputs, okay, you can refer to this diagram. I have to use some circuit here, for which the inputs are QA, QB, QC. Output is TA. Similarly, this is QA, QB, QC. This output is QA, output is QB, output is QC. So what I try to do is from QA, QB, QA, QB and QC, I try to get expression for TA, I try to get expression for TB, I try to get expression for TC. So that by using this circuit, some combination circuitry, I can move from 0, 0 to 1, 2, 3 up to 7, then back to 0. This is called up counter, right? So for that, what I am trying to do is, these are my outputs. Actually, these are flip-flop inputs. But with respect to this circuitry, that is, by taking the present states into the consideration. For this circuitry, these are inputs. For this circuitry, these are outputs. Okay. So what we try to do is, we will use three variable K maps and we try to solve it. So for TA, TB and TC, what is this is QC, MSB, this is QB, QA, 0, 0, 0, 1, 1, 1, 1, 0, 0 and 1, all are ones. Then all are ones, the expression for, what is the expression for, this is for TA, so TA is equals to 1. Similarly, I can do for TB, what is TB is like this, and here it is QC, it is QB, QA, 0, 0, 0, 1, 1, 1, 1, 0, 0 and 1, it is 1 for 1, 3, 7. So it is 1, 3, 5, 7. So if I combine these four, what I will get is TB is QA. Okay. So next what I try to do is, I will take up the next K map, which is for the third output, which is flip-flop inputs. This is QC, this is QB, this is QA, 0, 0, 0, 1, 1, 1, 1, 0, 0 and 1. What I try to do is, it is 1 for 3 and 1 for 7. So it is 1 for 3 and 1 for 7. So if I combine them, I will get the expression for TC. I have entered the values of TC. This K map is for TC. I get the expression for TC. So the expression for TC is nothing but QA QB. Okay. From this, what I can do is I can draw the circuit diagram. So I take three flip flops. Okay. What are these three flip flops? A, B, C. Which is LSB, which is MSB. A is LSB. A is LSB from the table you can see. From the table, A is LSB, C is MSB. So I take A as LSB. This is flip flop A. This is flip flop B. This is flip flop C. What I have is all are T flip flops. So for all of them, I will give a common clock. Synchronous counter means common clock. Clock is same. Clock is same. This is called clock. So this output is QC. This output is QB. This output is QA. Now the input is TC. This is TB and this is TA. What we got is TA is equals to what I should do. TB is nothing but QA. TB. So I take TB. I take TB. I'll connect this to QA. Okay. Next, what I try to do, what exactly it says is QA, TC is QA QB. TC is QA QB. So I take QA further. Okay. Then I take a QC here. Of course, which is there here. Now what I try to do is, I'll take this two, I'll give it to the AND gate, which I will get it. Okay. What I am trying to do is just I am developing or I am producing QA. Is it QA QC? No. One second. What we need is QA QB, not QC. So what we try to do is just remove this. This you are connecting it to. What I try to do is this we are connecting it to B, not C. There is no connection here. What I try to do is just I remove this. Okay. So what exactly that I can do now is just I can draw a line. Okay. So this is your QC. So this is your QC. This is your QB. This is your QA. Okay. So QA QB. This is your QA QB. Okay. So what we did? We are getting the flip-flop inputs from the outputs QA, QB, QC. Okay. And if you look at this, what is this circuit? This is a combination circuit. For this, what are the inputs and what are the outputs? For this combination circuit, for this AND gate, the inputs are states. What are the states possible? QA, QB, QC. What is the outputs possible? What exactly the outputs are nothing but TA, TB, TC. Okay. So for TA is always 1, whereas TB is QA, whereas TC is QA, QB. I got it. So for this direct connection, for this is always 1. So what I need to do is I will take TA, I will connect it to 1 forever. So TA is made 1, TB is QA, TC is QA, QB. If I make all these arrangements, then once if I give the clocks, what exactly is going to happen is that the circuit will move from one state to the other state. That the states that we are looking for are 0, 0. This is what exactly the clock look like. So we are giving the clock. Okay, this is a positive transition. For each and every clock pulses that we are applying, it will move from 0, 0, 0 to 0, 0, 1, 0, 1, 0. Likewise, it will go to up to 1, 1, 1. Once this is done, it will repeat the sequence. So this is what exactly known as 3-bit up counter.